We are on the last chapter here, and we started it last time. We're going to do a few more examples of the stuff you're responsible for that we kind of did last time. Then we'll finish up some of the rest of the material just to make sure we covered it. All right, so we're talking about this chapter, I think it's 11, and it's kinetics. And remember, as we talked about last time, kinetics deals with really how fast or slow a reaction takes place. And that's usually what is sometimes referred to as the rate of a reaction. And a lot of times we look at something like the change in molarity over time, how the concentration is changing with time. We talked about chemical expressions, rate expressions. That's what I'm trying to say. We talked about rate expressions, which you can use an equation such as this. And you can write rate expressions for each of the reactants and products. Something like the rate is equal to -1 over the coefficient, the change in the concentration of A over the change in time. That equals -1 over B, which is coefficient. I'll learn the alphabet there. And the change in the concentration of B over the change in time. And that'll be 1 over C, change in the concentration of C over the change in time. These are negative here for our reactants. As we talked about, the reaction should be proceeding to the product side, which means the amount of our reactant should be decreasing with time, and that's what the negative is really there for. And that's different than our products here, which should be increasing with time. So we do not have any negative on that side of it. We also take 1 over the coefficient, and really what that does for you is take care of all the mold-mole relationship, the stoichiometry that's happening in that particular reaction. And it kind of does it all together, both the stoichiometry and really the kinetics part of it. The deal here is typically when you calculate the rate here, which is the average rate, that is usually a positive number. So when we do something like the change in the concentration of A, which is our reactant, because it's decreasing with time, that means that when we take our final concentration of A minus our initial concentration of A, our final is going to be less than our initial concentration, which will give us a negative number for that change. And that, again, negative, and the negative that we put here in front for our reactants will turn our rate into a positive number, which is what we're looking for. On the product side, we don't need the negative again, because when we do the change of our product and we take our final minus our initial, our final should be more than what we started with, which would yield us a positive number, and thus positive and positive will give us a positive rate. So we can use the rate expression really to figure out how everybody is changing with times in a particular reaction. You really just need one piece of information to do that. Either you need to know the rate, or how maybe a reactant is changing, or a product is changing, and you basically figure out pretty much how everybody else is changing in that particular reaction. As we did a couple examples there with some numbers, you basically just kind of pull out the two pieces that you're interested in, and the rate for each of them should equal each other. So you could then relate it to what you're looking for. We then moved into the rate law, which is a little bit different. When we have the rate law, it looks something like this. The rate is equal to K, A to the X, and B to the Y. One major difference between, say, a rate expression and a rate law is the rate law is only concerned with the reactants. So there's no products in a rate law. So it's just the reactants that you're looking at. And unlike the sort of rate expression or other things, these guys up on top are what are referred to as the orders. And they are basically found experimentally. A rate law is going to be found pretty much experimentally. As we saw, and we looked at some examples, just some generic examples last time, that basically you think of the orders as sort of the proportion of each of those reactants that you need to maintain a specific rate. We also talked about, if you understand the rate law and the orders of your reactants, you can sort of manipulate, for example, experiments to your benefit. So we talked about that, if you needed to maybe speed up a reaction, you could look at a reactant and change the concentration And just by, for example, doubling a concentration in a particular rate law sort of system, it may actually double the reaction and may occur twice as fast. And the same thing can be said is if you needed to perhaps slow down a reaction as maybe it's happening too fast, you could also play with the concentrations. And depending on the orders, you could slow down that reaction as well. Now, depending on the individual orders for each of the reactants, one reactant may have a greater or more drastic effect on sort of the rate of the reaction. So you might want to play with that one versus the other one, which may not have as much of an effect. How we determine these guys and the overall order of the reaction, which is found by adding those together, gives us our overall order. We find these experimentally, and typically what you are given is a table of concentrations of your reactants and initial rates. And typically speaking, you will have a number of experiments in that table. Maybe 3, maybe 4, 5, 6, maybe a ton of different experiments. But ideally what you want to do, as we did at the end there, is go to the table and really find 2 entries where one of the reactants remains constant in terms of their concentration and the other one varies. And most people, mathematical approach is usually a good move on this, where you can take rate 2 over rate 1 equals RK A to the X, B to the Y, and K A to the X and B to the Y. Once again, it doesn't mean necessarily you take the first and the second entry, but you look for 2 entries where, again, we have sort of one concentration that remains constant. What this will allow you to do is basically figure out the orders of each reactant sort of individually. You'll end up with something like, 4 is equal to 2 to the X, and X is equal to 2 in this case. You'll get something like that. If it's not a nice, pretty number that you can really kind of probably figure it out, as we talked about, you could always take the natural log of both sides. And when you do, the X comes down, and then you could divide the natural log to the other side. You'll get your same answer. So if you end up with something that is not a pretty number, that is sort of what you can do. To try to get yourself maybe whole numbers, a lot of times it's a good idea to put the entry in the table that has the larger rate up on top, and that usually will give you kind of more whole numbers rather than decimal numbers. So that's usually a good idea to keep in mind as you're putting it in there. Technically speaking, you could do it either way. It doesn't really matter, but if you want a little bit more whole numbers, maybe manageable sort of numbers, usually if you kind of put the larger rate guy up on top, that usually gets you kind of those numbers where you can kind of probably just look at it and sort of figure out what the orders are. A reminder as well, it is possible to have a 0 order. And again, anything to the 0 order is basically 1. So that is possible as well to sort of get that. Any questions on any of that stuff there that we did last time? So as we saw there, rate laws is always found experimentally. The reaction order, when we write rate laws, again, is all about the reactants. Really, no products is usually included in there. And unlike a lot of things in chemistry, we do not get those orders directly from the coefficients, as we can see in the example we did there at the end. By the way, also, as like we did at the end there, once you get the completed rate law with the orders, you then can go back and actually solve for the value of the rate constant. And you could do that by basically just putting into your rate law any of the entries from the table, and they will give you the same value. If you use any of the entries, because it's a rate constant, which means it should be the same number no matter which experiment you're looking at. Any questions on that there? All right, so let's take a look at this one. The rate equation for the reaction of NO with ozone is the rate is equal to K times NO and O3. If the rate is 6.6 times 10 to the minus 5 molar seconds, when we have those concentrations, what is the value of the rate constant? So I'll just take a moment there and come up with that. Okay, so let's take a look at this one. We obviously have the rate law already given to us here, which is the rate is equal to K, NO, and O3. Again, if nothing is written there, it is assumed that the orders are 1 for each of those. So the overall order here would actually be second order by just adding those together. Gives us our overall order of the reaction. In this case, we are given the rate. We have the concentrations of each of those, so we could actually solve for K. To solve for K, it would be the rate divided by the concentration of NO and O3. A reminder that we don't have to do it in this case, but if there happens to be, like it was second order, one of those, or third order, or something like that, you would obviously have to take that into account here when you did the math. Here we'll put in our values. Our rate is 6.60 times 10 to the minus 5 molar seconds divided by our NO, which is 1 times 10 to the minus 6 molar, and our 3 times 10 to the minus 6 molar. Here, we'll punch that in and see 6.6 using our exponent button, 1 to the minus 6 and divided by 3 to the minus 6. Looks like a number with a lot of zeros. So say that looks like 2.20 times 10 to the 7. Now, in terms of units, if we look and see what happens here, molarity up on top and one of the molarities there on the bottom will cancel each other. And this will leave us 1 over molar seconds as our units, are sometimes, again, written something like that in terms of the units. And as we will talk about, those are the typical units that you find actually for a second order reaction overall from the rate constant. So one of the things that will allow you to identify sort of the type of reaction that you're dealing with is actually the units that you see associated with the rate constant. And these are typical units that you find for a second order overall reaction, say versus a first order, which would be slightly different. Any questions on that there? So again, sort of the larger the rate constant, kind of the faster reactions, the lower the rate constant, a little bit slower the reaction would take place. All right, so why don't you try one here? Why don't you find the orders and figure out the rate law here and the value of the rate constant. So based on the information in the table, see what you come up with. Okay, so let's take a look. So again, when you have a table like this, you pretty much need to use the table to figure out the orders first of each reactant. And then once you have that, you can then figure out the value of the rate constant. You could start with sort of like a generic sort of rate law for this. The rate in this case would equal K times our first reactant here, and we'll just call that to the X. And our second reactant here, we'll call that to the Y. So the goal here of the table is to figure out what the X and the Y is, which are the orders for each of these. And when we go to the table, what we're looking for, again, is 2 entries where one of them stays the same concentration, the other one varies. So if we look at experiment 1 and 2 in this case, our first reactant stays the same while the other one varies. So that's where I'm going to start. I'm going to look at experiments here, 1 and 2. And again, it's sometimes a lot easier mathematically looking at the numbers to find the one that has the larger rate of the two there that you chose. And again, just put that information up on top. So that's what I'm going to do here. I'm going to put number 1's experiment on the top. And what we're using, again, is that rate 2 over rate 1 equation that we saw a second ago, basically. And again, this is for 2 entries here into this table. So if I do that, starting up on top here, I got 2.2 times 10 to the minus 4, and that's going to equal my K. My concentration, my first reactant here is 0.08 to the X. My second guy there, 0.034 to the Y. And again, that is pretty much all experiment 1's information up on top. We're going to do the identical thing here with experiment number 2, put it on the bottom, which will give us 1.1 times 10 to the minus 4, k 0.08 to the x, and 0.017 there to the y. There's not any questions on where those numbers came from. At this point, we're going to do a little math here. So if we divide this out, that looks like we're going to get a 2. On the other side, that is the rate constant, and that is the rate constant. So although we do not know what the value is, it is a constant, which means it should be the same number on top and bottom, which means they will cancel out. In this case, we do not know the order of this guy, but it is the same reaction and the same reactant in this reaction, which means the order for both of those guys should be the same, although we don't know what it is at this point. That means that those guys should also completely cancel out. That leaves us just our last guy there that will not completely cancel out, but basically 0.034 divided by 0.017 should give you a 2 to the y in this case, right? At this point, you could probably just visually see it. A nice whole number there that in this case, y would equal 1. Any questions on that there? Now that we did it here for our iodide, we now want to really keep that one constant and vary the other reactants. So going back to our table, experiments 2 and experiments 3 there, we'll keep that one constant and vary the others. So we'll come back here and look at experiment 2 and 3 in this case. Once again, I'm going to choose experiment 3 to put up on top since it's the larger rate. So just like I did previously, everything from experiment 3 is going to go up on top. That will give me 4.4 times 10 to the minus 4 equals k 0.16 to the x and 0.017 to the y. Now everything from experiment 2 goes on the bottom, which is 1.1 times 10 to the minus 4, our k 0.08 to the x, and 0.017 to the y. Once again here, we're going to do a little math, and we're going to get some numbers here to work with. And if we do that, this is going to give us a 4. Once again, the rate constant should cancel. These guys here, when we divide it, should give us a 2 to the x. And once again, these guys should completely cancel as they're the same. That, in this case, you could probably also just visually look at it and see, in this case, that x does equal 2. Any questions on how to use the table there to get the orders? Now that we actually have the orders, we could write the completed rate law in this case, which would be the rate is equal to k times S2O82 minus, and that would be to the second order, times our I minus, which is to the first order here. And again, we don't have to put the 1 there up on top. The overall order in this particular reaction is going to be 2 plus 1, which means that technically speaking, overall, this is a third order reaction when you add up the orders of each of the reactants. Any questions on that there? Now that we have that, we can actually solve for k in this case. So to finish it out here, to solve for k, k would equal the rate divided by the S2O82 minus, and once again, we do have to square it, times the I minus. So we're basically just taking these two guys and dividing it over to the other side and solving for k. Now at this point, as I mentioned before, you could choose any experiment that you like here to put the numbers in to this. As long as you don't mix and match, you're good to go. So I'll just use experiment number 1 here. And if I do that, I will have up on top 2.2 times 10 to the minus 4 molar seconds divided by 0.08 squared and 0.034 in this case. Yeah. And if I do that there, we will get looks like 1.01. Now, in terms of the units, molarity up on top and one of the molarities there on the bottom will cancel, and that will actually leave us units of 1/molar squared seconds. And again, the molar squared comes from there, as you need to square that guy right there. Yeah. As you can see here, the units of the rate constant for a third order reaction are different than what you see for a second order reaction, and they're different than what you see for a first order reaction. So by looking at the units associated with a rate constant, you could determine the overall order of a particular reaction. Any questions on that one there? So it's very similar to what we did at the end last time. So let's do one more just to make sure. I think you have this one. Let's do this one, I think. Same thing, figure out the rate law. Okay, so once again here, we're going to use the table to figure out our rate law. We'll just start with a sort of generic one here. Our rate is equal to K times our reactants here. I'm going to call that guy to the X and take my other reactant and call it to the Y. So I'm going to go to the table here and again, look for two entries where we could keep one constant. And in this case, it looks like 3 and 4 will keep that guy constant right there. So looking at experiments 3 and 4, I'm going to put 4 up on top as it is the larger one here. So that's going to be 21.6, by the way, times 10 to the minus 7. So in case you missed it, that's kind of important there in the table. That each of those are to minus 7. Which won't screw up too much of your answer till the very end. So if you didn't see it, you'll be good till the end. But when you go to calculate something like the rate constant, you're not going to be correct in terms of your answer. So we'll do that is equal to our K times our 0.2 to the X and our 0.0404 to the Y. Here we'll put everybody from 3 on the bottom, 10.8 times 10 to the minus 7, K 0.2 to the X, and 0.0202 to the Y. So if we do that there, you'll end up with 2 here is equal to, once again, these will cancel, these will completely cancel, and we'll have a 2 to the Y here as we do the last part there. And here that would give us Y is equal to 1. So the order with respect to the NO2 minus is going to be 1. We'll now go back to our table and just quickly looking at it, it does appear here we could go 1 and 2 and keep that guy constant. So looking at experiments 1 and 2 in this case, we go with 2 up on top, going to give me 32.3 times 10 to the minus 7 equals K 0.06 to the X, 0.2 to the Y. And again, that is everything from experiment 2, everything from experiment 1 there on our bottom. And again, here we'll do a little math and we will get here about 2.99 is equal to the cancels. This will give us a 3 to the X, and this will cancel. That's pretty close to 3, I would say. So here our X is going to equal 1. Once again, if you wanted to, you could take the natural log of 2.99 and then divide it by the natural log there of 3. And you'll essentially get 0.997, which is essentially 1. So if you want to do a little rounding here, it's not going to hurt too much here. Any questions on that there? So in this particular case, that means our rate law will look something like this. The rate is equal to K times our first guy here and our second And overall order here going to be 1 + 1, which is a second order reaction. Now we could solve for K once again by choosing any of the entries. So I'm going to choose the first one to put it in there. K in this case will equal the rate divided by NH4 plus NO2 minus. So this is where it will make a difference if you did not do the times 10 to the -7 part for sure. You'll get your molar seconds divided by our 0.02 molar and our 0.2 molar in this case. So if we do that, going to get us a 2.7 times 10 to the -4 unit-wise molarity on top, and one of the molarities there on the bottom will cancel, gives us 1/molar seconds, which once again is what we saw earlier for a second order reaction. Those are again the typical units that you see there. You can almost just count the letters as 2 letters, second order. The other one was 3 letters, third order. First order, 1/seconds, 1 letter, basically. So you can kind of count the letters in a lot of cases, and it'll kind of tell you the overall order. Any questions on how to do this here? Obviously, this is what we were doing at the end last time. All right, so from this point back, yes, you're responsible for. Yes, for the final. We're going to continue on, though, and talk about some other kinetic stuff, which is good information, especially if you're going to take 200B about first order reactions, which is what nuclear decay follows. And we'll cover some of this stuff, but they will not be on the final, any of this stuff from this point forward. All right, so there are different types of overall. Yeah, so whatever I just said now. So basically the rate expression and what we just did, which is kind of what we did last time. So everything kind of what we did last time, we just want to do a couple more examples here today of it, is what you're responsible for. So the rest of it you won't be in the for the final. All right, so first order reactions are common sort of orders of reactions. The 3 sort of common orders of reactions that you come across are first order, second order, and 0 order reactions. And really a lot of the reaction orders are based on, if you think about most reactions that you probably have come across, most reactions that you come across usually will have maybe 2 reactants, maybe 1 reactant, maybe 3 reactants if it's kind of crowded, but you usually don't have a lot of reactions where there's like 4, 5, 6, 7 different reactants all happening at once. So these are the common orders overall for reactions that end up, because in order to get, technically speaking, really high orders of overall reactions, you would need a lot of reactants probably reacting all at once, and that typically doesn't happen. So usually kind of that first order, second order, 0 order sort of arena is sort of where these overall orders sort of end. So when we have a first order reaction, there's a couple really important things about first order reactions and all these sort of specific orders. And that is the rate law here would be the rate is equal to K times the concentration of A. So one way that you could get a first order reaction is to have only 1 reactant where the order of that reactant is 1. You could also get a first order reaction by having 2 reactants where 1 reactant is 1 first order, the other one is 0 order, right? So that's possible as well, and still have an overall sort of first order reaction. So as I've been saying, as we're going through some of these examples here, if we were to take the rate law here and solve for K, which is what we do here, and just look at the units of the rate constant, these are the typical units that you find for a first order reaction that has a rate constant, and they are 1/seconds, or reciprocal seconds. They're really 1 some unit of time. They don't necessarily have to be seconds. It can be 1/minutes, 1/hours, days, weeks, whatever it may be. But very common when you do experiments, you don't sit there for weeks on a reaction, right? So a lot of times you measure in seconds. So that's a very common sort of kinetic unit of 1/seconds. but it doesn't necessarily always has to be sort of seconds as a units. And if you were given the value of a rate constant, which is very common in kinetics type problems, they will kind of give you the value of the rate constant with the units, but very often they won't in blinking lights go, hey, this is a first order reaction, or this is a second order reaction. So they assume that you can figure out what order reaction it is based on the units that you see associated with the rate constant. And why that's important is because for different orders of reactions, there are different equations that you want to use or formulas that you want to use, which are sometimes referred to as integrated rate laws. And that is basically this equation right here. And this is really the sort of time and concentration dependence sort of formula. And that is the natural log of A is equal to the natural log of A naught minus KT. This is like your final concentration. That is like your initial concentration. That is your rate constant. And T here is actually time. So not temperature or anything like that. So the little T here is time. And though that is the integrated rate law for a first order reaction. And there's also a half-life equation we will see where the half-life is the natural log of 2 over the rate constant. The half-life, as we'll talk about, is basically the time it takes for half of whatever you have to kind of go away. So if you started with 10, after the first half-life, you would have 5. After a second half-life, you would have 2.5. And then after a third half-life, I would need a calculator, but you keep dividing by 2, and then you'll have that much left at that point. So kinetics is all about a lot of times graphs. So you see a lot of graphs in kinetics. And a lot of times when we graph things, we look for sort of a linear relationship in a reaction. And you could take the integrated rate law, for example, here, and you could rearrange it and go the natural log of A is equal to minus KT plus the natural log of A naught. And this is actually written in the form of everybody's favorite, y is equal to mx plus b. So this will give you a linear relationship with your kinetics information. And on the y, as you can see here, you would graph the natural log of A. And on the x here, you would graph time. And that should give you a linear line, basically, or a linear relationship that will occur. And as you can see here, the slope of that line will equal negative of the rate constant. That line that is drawn there is a straight line, and that line has a positive or negative slope, that line. It has actually a negative slope, yeah? So this negative slope means that when you get the slope of that line, that's going to be a negative number and equals negative K, which means your rate constant will be a positive number. So negative will get you to a positive number. So this is the linear relationship that you typically will see for a first order graph. You will sometimes see for a first order graph this plot here, which is the concentration versus time. And as you can see, as time goes by, we are losing our concentration, right? So it's getting smaller as you go through there. So typically speaking, when we look at first order, and first order reactions are really important ones. And as I mentioned before, if you take 200B, the nuclear chemistry chapter, when you deal with kinetics, it's all about first order reactions. So you'll use these reactions. So the units associated with the rate constant is important. The typical graph that you see is usually very important for first order. This integrated rate law, which allows you to figure out, how concentration is changing with time. And also the half-life equation is really important. A lot of times you will have to use both of these equations together. So a lot of times you will sometimes have to use both of these guys together. So for example, they may give you the half-life and not the rate constant, but give you some other information. And a lot of times you'll have to use the half-life equation to figure out the rate constant. And once you have the rate constant, you can go into the integrated rate law and solve for whatever you are looking for. So let's take a look at one. I want you to try. The reaction is first order with a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds. How long will it take for the concentration to decrease from? Okay, so a couple of things here. Obviously, they were nice enough to tell you it's a first order reaction, but a lot of times they will not be that nice. And we would know that it is first order based again here on the units that we see associated with the rate constant. So those are our 1/seconds. So that means that it should default you to really the first order integrated rate law here, which is our final concentration equals our initial concentration minus KT. In this case, we do have our rate constant of 2.8 times 10 to the minus 2 reciprocal seconds. We have our initial concentration here of 0.88 molar. We have our final concentration here of 0.14 molar. So putting these in would give us the natural log of 0.14 equals the natural log of 0.88 minus our 2.8 times 10 to the minus 2 reciprocal seconds and time. Personally here, I would take the natural log of 0.14 and then subtract that guy to the other side. And if you do that, a little natural log here, 0.14 minus the natural log of 0.88. Going to get us a negative 1.838279 equals negative 2.8 times 10 to the minus 2 reciprocal seconds times time. Now we're going to divide this, not only the number, but also the negative to the other side as well. So dividing that there, going to get us about 66 seconds here. And obviously the seconds comes from the units of our rate constant. It's 1/seconds, but when we divide it, it flips to the top of the seconds, right? Question on that one there. All right. Good. Good. Yeah. All right. So as I mentioned before, there are half-life equations and specific ones for different orders reaction. And here, this is again also an important one, as I showed earlier, for first order kinetics, which again is used for nuclear decay or radioactive decay. It's the natural log of 2 divided by K. If you take the natural log of 2 on your calculator, that's where the 0.693 comes from. That's what you get. And here, if we wanted to figure out our half-life here, we would basically just plug it in. So we take the natural log of 2 divided by our rate constant. And that would get us, in this case, natural log of 2 divided by 5.7 to the minus 4. And that's going to get us about 1216 seconds as our half-life. And that's roughly like 20 minutes or so. So every 20 minutes, this guy is going to lose half of what it has as it goes through there. And once again, here, we do know that this is first order based on the units that we see there of reciprocal seconds in our rate constant. Questions on that one there? So as you can see here, this is our half-life demonstration. And again, we do lose half every time there is a half-life. About 10 half-lives, pretty much everything is gone at that point. So why don't you try one here? The reaction here is first order, rate constant of 2.9 times 10 to the minus 4. Find the concentration of our SO2Cl2 after 865 seconds if we started with 0.0225. Okay, so once again here, if they didn't tell you it was first order, we would be able to figure that out by our units that we see here on our rate constant, which again are reciprocal seconds, which tells us that it is first order. We do have our initial concentration here of 0.0225. We're actually looking for our final concentration, and we do have our time of 865 seconds. So our natural log of A equals our natural log of A naught minus KT. Natural log of A will equal natural log of our initial 0.0225 minus RK 2.90 times 10 to the minus 4 reciprocal seconds, and our time, which is 865 seconds. This also brings up a really good point when you ever use this equation, which you might down the road. You always want to make sure that the unit of time here, both in your rate constant and the time part, are the same unit. So it's also very common that maybe your rate constant is in, say, units, say, of days, and maybe the other one's in minutes or something like that. So you do always want to kind of check the time aspect of it, as they may not always be in the same unit. It doesn't really matter what unit you put them in, as long as they are the same. So in this case, they are the same. They're both seconds, so everything will cancel out correctly. So we're just going to clean up the right-hand side here, a little natural log of 0.0225 minus 2.9 to the minus 4 times 865. Going to get us the natural log of A is equal to minus 4.04509. To get rid of the natural log on both sides, we're going to take the E. That will get rid of the natural log on that side, and we're not going to do anything to the sign, so we're just going to take it the way it is. On most people's calculators, that's like a shift or second button and the natural log button, and we'll put our number in there. And that's going to give us a concentration of 0.0175 molar, which is less than what we started with, which is good. If we end up with more, that would be bad. It's going in the wrong direction. Any questions on that one there? So these are the equations for first order kinetics, which again will pop up again for you if you take 200B in nuclear chemistry, where all radioactive decay pretty much follows those two equations in first order kinetics. But there are some other orders which are important. So let's take a look at some of the other orders and some of the important things that we see for those guys in the graphs. So for a second order reaction, which once again, you could get in a couple of ways. One reactant that is second order. You could also obviously have two reactants that is first order in each, which gets you second order, or two reactants where it's second order and zero order. If we just solve for the rate constant like we did previously and look at the units, as we saw in some of those examples, these are the typical units that you find for a second order reaction overall. 1 over molar seconds. Once again, much like first order, the unit of time doesn't always have to be seconds, but it's basically 1 over molar or some unit of time. But seconds is very, very common. There's also an integrated rate law for first order or second order here, which is 1 over the final concentration equals 1 over the initial concentration plus KT. And as you can see here, the half-life equation is also a little bit different than what we see for first order. It is 1 over K times the initial concentration. So unlike first order, which is independent of the concentration that you start with for the half-life, the half-life here is actually dependent on the initial concentration that you have. So it will have an effect on the actual half-life of it. Just like the other one, we could rearrange this equation right here in the form of a straight line, which would give you 1 over A is equal to KT plus 1 over A naught. And that's going to be your Y is equal to MX plus B. So as you can see on the graph there on the bottom, what we graph on the Y is 1 over the concentration. Once again, here on the X, we graph time. And that will give us a linear relationship here for the second order. This is actually a positive sloping line. which means that the slope here will actually equal the value of the rate constant. So much like first order, there are several things that are good to remember about a second order reaction. The units you see for the rate constant, your integrated rate law that involves concentration and time, your half-life equation, and again, the typical graph that you see for a second order reaction. Any questions on that one there? The last sort of common order of reaction is a zero order reaction. And in a zero order reaction, we could get it by having one reactant, that is to the power of zero, actually. And that will obviously give us a rate law that is equal to the rate constant, which means much like first order, second order, the units associated with a zero order reaction is actually the same one that you find for the rate constant, which is molarity over seconds. Which again is different than what you see for first order or second order as well. Also has an integrated rate law, which looks just like the first order, except there's no natural log. So it's just the concentration. The final concentration is equal to the initial concentration minus KT. Also has a half-life equation, whereas the initial concentration divided by 2K. And much like our second order, our zero order is also affected by the initial concentration. Only first order is independent of the initial concentration. If we take our equation there, just like the others, we can rearrange it into the form of a straight line, giving us our y is equal to mx plus b. And the typical graph that we graph for a zero order is the concentration on the y and the time on the x, giving us a linear line where, again, we got a negative sloping line. So our slope in this case is equal to negative of the rate constant. So much like the others, those several things are important for zero: units, rate law, and our half-life, and again, the graph. You may also recognize this graph as the same graph that we saw for first order, except in this case, it gives us a linear relationship. For a first order, you do not get the linear relationship. You get that one that's decreasing with time that we saw when you graph that. So that is the difference between them. That also means that you can, if you do a kinetics experiment, for example, do graphs and graphically determine the order of the reaction. What you would do is do all three of those graphs for your experiment, and whichever one had the most linear line would be the order of the reaction. So graphically speaking, you can actually take your kinetics information and do the three different graphs and figure out what the order is, and also get the rate constant at that point from the graph. So that's one way that you can kind of do it. You could also do similar to what we did the other day, and as I talked about, sort of just measure absorbance values over periods of time and make graphs and figure it out that way. So here's just a nice little table that summarizes the three different orders that we looked at, in case you ever need it for future reference. If you're good at math and you can't remember the half-lives, you could use the integrated rate law and actually solve for the half-lives by taking the final concentration would be the initial divided by 2 and solve for time. If you're ever bored, that's how you get to these guys here. Any question on specific orders of reaction? All right, the last thing we're going to talk about here in kinetics is the idea of temperature and how it affects the rate law or the rate. These are energy diagrams, and there's two different energy diagrams here. One's an exothermic reaction, which means energy is being given off, and one's an endothermic reaction, which means overall energy is being absorbed. This is our reactants, that's our products. So once again, whenever you have reactants higher in energy than your products, overall energy has to be given off as a result of that, which is why it's exothermic. You could calculate the delta H of the reaction by taking the difference in the energy of those two spots, and that's the enthalpy, or change in enthalpy of a reaction. Here our reactants are lower in energy than our products, so to get up there, you got to kind of put energy in to do that. And again, you can calculate the delta H by taking the difference of those two. This will end up with a delta H value that's negative, which means it's exothermic overall. This will end up with a delta H value that's positive. But more importantly, when a reaction takes place, all that happens is we break bonds on our reactant side and make new bonds on our product side. But in order for that to happen, a couple of things need to occur. You need to have collision between molecules, and they do need to hit each other in the right sort of location. And they also have to hit each other with the right amount of energy. And there's always a barrier of energy as the reactants are trying to make their way up and over to the other side. And that is what is referred to as the activation energy. It's the hill that the reactants has to climb in terms of energy to get to the other side. It's the minimum amount of energy that's required for that reaction to take place. So as the reaction is taking place, you got everybody breaking bonds, starting to make bonds. It gets to the very top of the hill here, and this is what is sometimes referred to as a transition state. It is the highest point in energy in the reaction. And as you might know, high energy is not really optimal, right? It's really an unstable situation. So it creates this sort of complex up on top, which is very unstable because it's the highest point in energy. It doesn't hang around a very long time, and it will kind of drop down to the other side relatively quickly to make your products. Now, the hill, or the activation energy, is the barrier of our reactants getting to our products, and also has a big effect on the rate of the reaction. So obviously, if we have a really big activation energy, there's going to be a less proportion of molecules that have enough energy to get up and over to the other side. It's going to take longer probably for that reaction to take place than if you had a smaller hill. One way that you could lower the activation energy is to add a catalyst to a reaction. We add a catalyst to the reaction. It finds an alternative pathway for that reaction to take place. Ultimately, what it does energy-wise is it lowers the activation energy. So the hill gets much smaller, and that allows a greater proportion of molecules to have enough energy to get up and over to the other side, and it usually results in the reaction occurring a lot faster. So in terms of temperature, we'll take a look at this equation here. Perhaps we get to it. So this equation here is what is sometimes referred to as the Arrhenius equation, and it allows us to calculate something like the activation energy if we know some temperatures here. So this is the rate constant at temperature 2. That's the rate constant at temperature 1. These are the temperatures, and they do need to be in Kelvin for everything to cancel out correctly. R is our gas constant, but it is the one that involves energy, 8.314 joules per Kelvin per mole, and that is our activation energy. So you can use an equation like this if you have two pieces of information. There's also a graphical version of the Arrhenius equation where you could do the Arrhenius plot and figure out the activation energy through the graph. The ultimate idea here in terms of temperature and how it affects the rate of the reaction is obviously, since there's that energy barrier that everybody has to climb to get to the other side, typically speaking, when you do increase the temperature of a reaction, what you're doing is adding more energy, right? And now what happens is you have a greater proportion of molecules that have enough energy to get up and over the hill to the other side, and that usually results in a faster rate occurring. So for example, if you raise the temperature about 10 degrees Celsius for a lot of reactions, that's enough to just double the speed of the reaction or have it occur twice as fast as it normally would. Opposite of that is kind of like what you did in your experiment there. You threw everybody on ice, right? Instead of the hot water bath. When you throw it on ice, you're removing energy from the equation, and that means you're going to have a much lower proportion of molecules that have enough energy to kind of get up and over the hill to the other side, and that usually results in the reaction happening slower. So that's ideally what you should have saw. In the hot water, it should have turned blue quicker. In the cold water there, or ice bath, it should have took a lot longer for it to do than it did, say, at room temperature. Any questions on that there?